Okay, well, if you want to wait like 30 minutes, we can do with it. Just go on. Okay, so now you're running GNOME. That's easier. But is it in any way? Is it in any way possible that this is just turned off? Okay.
Really?
I don't know. It looks turned off, doesn't it? It's completely off. I'll touch this, and I will not change any. I just want to look at it. So VGA it is. Notebook VGA. So probably VGA should work.
Yeah, he does.
So I think we actually just needed to switch this to HDMI, but we are not allowed to do that. So just run it from your laptop. Andrea? Yeah? Did that display just come out on its own? No, I touched it, but I didn't. I just touched the display to wake it up, and I didn't touch any of the settings, and I'm not going to. Not something. So you so you use VGA and just magically works, right? Yeah, I think it's just configured to just use VGA. If we switched it to HDMI, they would work. But we are not going to do that because we are not allowed to. For some reason. Andrea? Yes? Tell me. Sorry. No, they're not. The number is over there in the corner. But Pavel is there.
Yeah.
You just tell him that. Okay. He doesn't speak to you for some reason, but the number for the guy, for the technician, is down there. Okay? Yeah. If we need it. Awesome. If you could set your external display to 4:3 resolution, not revolution. I know how to do that in GNOME. So just S, and just and now this is start your presentation again. If I can get the cursor back, it should display just fine. Oh no, sorry. Yeah, see that's slightly better. Did you get the clicker?
Yeah.
And then for the
clicker, you just need to plug this in, and it will just get the.
We don't see it here.
Let's try to.
You need to plug it into USB?
Into any USB port. And try switching to the next one.
Awesome. Sweet.
So I guess we are 1 minute over, 1 minute late. You can unmute and start. Do you want me to introduce you, or will you do it yourself? Maybe it's better if you do it yourself because we're short on time.
Well, we do it.
Yeah, just unmute. You can get started.
Okay. Okay, so hello, my name is Maxime Coquelin, and we speak with Victor today. We talk about how virtual networking, virtual machine networking can benefit from DPDK. So first, we will start with an overview of DPDK and Virtio and VirtUser. Then we will talk about the challenges that we can face when implementing Virtio into DPDK. And finally, we will talk about the new and upcoming features that are being introduced to address these challenges. So let's start with the overview. So DPDK is a set of user space libraries whose goal is to achieve fast packet processing. So it means data plane development kit. And the idea is to benefit from the flexibility brought by software in order to achieve a performance that is close to dedicated hardware solution like ASICs, for example. So the project is released under the BSD license. It supports multiple architectures like Intel x86, IBM Power 8, Telluride TechGX, and ARM v7 and v8 more recently. Most of the server NICs, server-grade NICs are supported from main vendors. Also, it supports now other kind of hardware, like crypto devices with a new crypto framework. And some parts of the DPDK project are being reused by a storage project called SPDK in order to have a vhost user backend emulating SCSI. So the talk will be about Linux, but DPDK is also supported on BSD. So I draw this timeline. So the idea is that I draw the main milestone. So in 2012, Intel released the first version of DPDK. It was stored on their website. So multiple companies started to fork the project and created a kind of fragmentation. So we have some drawing problems. So it's the year after, in 2013, a French company called Sixwind initiated the DPDK.org community. So they put in place servers, mailing lists, and Git repositories, so that other companies could start to contribute back to the project. In 2014, it was first released in DPDK was first packaged into a Linux distribution. So it was Fedora. So before 2015, only Intel architecture was supported. But hardware diversification started in 2015 with IBM and Tilera architectures being introduced. ARM followed the year after, in 2016, with and also with the crypto framework I talked in previous slide. And in 2017, it's not a technical milestone, but since we now support the project is now supported on multiple architectures. It's no more an Intel-only project. There is a decision to move the project under the Linux Foundation umbrella. So I draw the versions below, so I won't list all the versions. I wanted to highlight that since last year, the numbering scheme changed to year.months to give more predictability. And starting last version, 16.11, the decision was made to move to 4 releases a year because there is more and more contributions. So in last version, the project represented about 750,000 lines of code, split in 6,000 commits from more than 300 contributors. So the idea of this slide is to give a simplified comparison on how an application based on DPDK compares to a traditional application relying on a kernel networking stack. So the idea is to bypass the kernel, to do all the stuff in user space. So to access the NIC register directly, we rely on VFIO. So that the application can directly write into the NIC registers, and also the pages, the user space pages storing the packet are directly referenced by the NIC descriptors. There is no copy from user to kernel of the packets. So to achieve the best performance, DPDK relies on a number of system features, from which we have, it relies on CPU isolations and soon CPU partitioning. So the idea is to have dedicated physical cores that poll the NIC. And to do this polling, so as I said earlier, it relies on VFIO, or we could use also UIO, but for security reasons, we would advise to use VFIO. To have the best performance, we also rely on NUMA awareness. So the idea is that all the resources, the memory, the PCI devices, have to be on the same NUMA node as the physical CPU that is running the PMD threads. And also it uses huge pages so that we relax the TLB cache. And also the other advantage is that it avoids swapping, that we couldn't have with, that we cannot afford. So the idea is to avoid interrupt handling, to do polling mode, to have best latencies, and as I said earlier, to avoid switching from user to kernel mode, because, for example, syscall, some measurements made by Jesper Boer show that the time budget needed to perform a syscall is higher than the time budget we have to transmit a 64-byte packet at 10 gig line rate. So this slide shows the different libraries that the DPDK project is composed of. So we have a first set of libraries that are the core libraries that are used to do abstraction layer, packet representation, memory pools. The other main part is the PMD drivers, so all the NIC drivers. So they can be physical, like Intel, Cisco, or Mellanox NICs, or in our case, of what interests us today are DPDK support VirtIO and vhost PMDs. And the vhost PMDs relies on the vhost library, so that applications can either use the Ethernet API directly, the Ethernet API to be able to use the vhost device as if it was a physical NIC, or it can directly use the vhost API, which maybe provide some more flexibility. So now Victor will talk about VirtIO and vhost user.
Thank you, Maxim. So we have DPDK library, which is all about high performance, and in general, it's not related to virtual machines or virtual machines networking. It's a way to enable user space application on the host to perform very fast networking by implementing network stack in the user space. So it just happens that DPDK also support some kind of VirtIO devices, but let's see how we can achieve this kind of high performance, and just to give you some understanding about the speed and bandwidth and latency that we are talking about. We're talking about sending and receiving 10 million packets per second. When we're talking about smallest packets, and we want to achieve the bandwidth of order of magnitude of 10 gigabits per second. And at this speed, we have each packet, to handle each packet, about 200 nanoseconds, which need to be used also to copy and to handle all the needed stuff. But before we see how DPDK fits virtual networking in VMs, I want to show you some overview about how regular networking is done from virtual machines. So we have different options. One of them is device emulation, when we just emulate some simple networking card. And this approach works well, but the speeds which we can achieve is about 50 megabit per second with this approach. Another approach is direct assignment of networking card into VM, and then to give network stack in the kernel of virtual machine to handle the network traffic. This way we achieve about 500 megabits per second, and the main overload is in the kernel of the guest. Another possibility is much faster and is using VirtIO device. VirtIO is just virtual device that is supported by KVM and QEMU, and modern kernels, both in Windows and Linux, have inside them the driver for virtual I/O devices, and QEMU and KVM support these kind of devices by vhost. And what is the vhost? Vhost is, instead of emulating the network card in QEMU and user space, we have in kernel of host, we have some entity which we call vhost. It's just a thread that's running, and it communicates directly from kernel of host to the VM. Usually it's kernel of VM. And it can place packets and buffers to and from the memory of a guest operating system. So in this installation, it still runs the network stack in host machine, so it's a quite large overhead, but we eliminate the additional overhead which related to virtual machine layers. So we can achieve the same speeds of about 500 megabit per second with this installation. And to go to much higher speed, we have to use solutions like DPDK, which enable to the user application some kind of direct access. So how does it work? We have this virtual host in the which can access directly the physical memory related to virtual machine, and we have a possibility to send and receive signals about new buffers that arrive to and from VM. So we achieve it in one direction by IO event FD, the usual mechanism in the Linux kernel, and to signal guest operating system about new buffers that arrives, we use the protocol of IRQFD. And this in-kernel VirtIO emulation is really is the main mode which is currently used. When you use today virtual machine with VirtIO drivers, it's what usually means that we have VirtQ emulation on the host operating system, The QEMU handles all the control and negotiation and all the things around that not related directly to the data path. And the data and buffer themselves goes directly from the host operating kernel of host operating system to the guest. And this way we bypass the QEMU and anything which lowers the speed. And in kernel we can just pass the buffers between guest to tab device or directly to the NIC, and all the switching possibilities exist. So it just was an overview of what is virtual networking, and later I will explain how we want to introduce DPDK very high speeds into virtual machine networking. Another existing possibility which is very useful and is going much acceptance by enterprise and by industry is that we enable to third parties to supply their implementation of this vhost. So we call this vhost user, and QEMU has a new interface which enables user applications from third parties to supply this backend and to supply such functionality. And DPDK have vhost implementation in its library to support this, and this enables all communication like OVS and software switches and other features. It works very similarly to vhost in the kernel, just instead of using IRQFDs and event SDs, every signaling is going through Unix sockets, so it's slightly slower, but the main data path is still going directly from one user application to the guest, and all the buffers are just mapped to shared memory, and everything works smoothly. So Maxim will talk about some challenges that we currently see, and later we will explain how we going to address these challenges.
It's okay. Thank you. Thank you, Victor. So yes, we have a number of challenges that we need to address. So the first one and the most important one is the performance, because DPDK is all about performance. This is what we want to achieve. So the first, so we can split challenges in a trade-off of multiple aspects, and three of these aspects are the bandwidth. So the idea is that we want to achieve line rate, even for small packets, something that is not possible with the kernel today. Of course, we want to have a latency that is as low as possible. For example, with the 5G norm that is coming, this is becoming really important. And of course, the CPU utilization, because the more CPUs you need to achieve the best bandwidth and latency, the higher the price, the cost will be. So today, we invest much on bandwidth and latency, because that could be showstopper if we don't achieve the right performance at the expense of the CPU utilization. And to do this, we need to take into account the hardware architectures of the CPUs as much as possible. But the problem is that we have multiple architectures to support, and so it's a challenge because one optimization that you will do for one architecture like Intel could cause regressions on other like ARM. The second challenge is reliability. So especially for NFV use case, we cannot afford packet loss. But this is something that is hard to achieve, especially when we want to achieve the max performance, because Virtio is only relying on the CPU, so it's really CPU intensive. And any scheduling glitch can cause packet drops. So you need to have your PMD threads isolated from other possible perturbations as much as possible. The other challenge is the migration, because when we want to migrate from one host to another, QEMU save its states and restore them. But in the case of the host user, we have a third party, so that could be OpenVSwitch or VPP, and we need to ensure that the migration that will happen will be successful. So if you migrate from a new host to an old host, and that doesn't have the same version of OVS, for example, you could have started the first host with a feature set that is not available on the destination, and that would break the migration. And to achieve this, so this is ongoing work, but we need to rely on the management tool to ensure that when we start a host, we start it with the right configuration so that migration is possible with the other ones. So Victor, talk about security challenge.
Yeah. Generally, the security and high performance is a big trade-off. So since to achieve high performance, you need some kind of direct assignment of hardware to the user space, and you lose security. And using of VM is mainly in the scope of applications that want this isolation and security between VMs and between processes. In context of NFV, if you want every network function to be run in a different virtual machine, we need to supply both high performance networking between these virtual machines and high isolation, and it's quite hard to achieve. And all current implementation of networking between VMs required some kind of mediator in the path between VMs or between VM to the network card, and this mediator mainly just copies buffers from one memory to another memory, from one memory of one virtual machine to another, and by the way just checks if there is rights to read or write that memory locations. And to achieve zero copy, we need something else, since zero copy is required for high bandwidth, and it's problematic from security point of view, and later we will see how we propose to address this point.
Okay, so now we'll talk about the new and the upcoming features that we are working on to address these challenges. So, receive mergeable buffer. So this is not a new feature. So this is here since quite some time, but I will refer to this feature in the next slides. So I wanted to give a brief overview of the feature. So the idea of receive mergeable buffers is to make possible to receive packets that are larger than the VirtIO descriptor's buffer size. So, for example, here you have descriptor 0 that transmits one packet. So we have num buffers equal 1, and we want to transmit a packet after this that fits into 3 descriptors. So we need to set the num buffer field of the VirtIO net header to 3. So this allows to transmit large packets, but it has one disadvantage, is that it introduces some extra cache miss, because even if you always only send small packets, you will have to parse this num buffer field, and even if we know that it will be equal to 1. Second feature is indirect descriptors. So it had been introduced in 16.11. When you have direct descriptor chaining, if you want to transmit a large packet, if the VM want to transmit a large packet, it will use multiple descriptors that will be chained. So for example, here we chain from descriptor 2 to descriptor 0, etc., etc. So the problem is that when you only send large buffers, you will, if all packets you will send takes 4 descriptors, you will divide your ring capacity by 4. And with indirect descriptors, we add a new table so that whatever the size, we fill this table with the number of descriptors needed. And whatever the size, the ring capacity will be the same. So, as I said, it increased. The advantage is that the ring capacity is increased, and we see some improvement when transmitting large number of large buffers, large packets. But we also noticed that it improved zero packet loss when your system is not fine-tuned. So, as I talked earlier on the reliability challenges, small scheduling glitches can cause packet drop, and so even for small packets, we always use 2 descriptors today, one for the VirtIO net header and one for the buffer descriptor. And by using indirect descriptor feature, we double, in fact, the ring capacity. But it has a small cost because you have one more level of indirection. So if you don't care about packet loss, you will notice performance degradation of about small performance degradation, around 3% in my measurements. Another feature is that has also been introduced in 16.11 is vhost DQ 0 copy. So by default, what we do is that when we receive on the host side a buffer from the guest, a descriptor from the guest, we perform a copy from the buffer descriptor to the mbuff buffer. Mbuff being the packet structure in DPDK. So the idea is simple. It's just to reference this descriptor buffer directly into the mbuff. So for VM to VM, we see a big performance improvement for large and standard packets, but it has a very limited scope today. So it's a little hacky because the mbuff structure is not thing today to point to external buffers. So it does not. So it works only for VM to VM today, and because when we transmit to a NIC, the NIC does not release the descriptors, the packets as it releases them by batch. So sometimes we can run out of descriptors into the virt queue. So there are some work going on to improve this situation. Another feature is the MTU feature. So the idea is for the host to share the maximum supported MTU. So it can be used, of course, to be able to set the MTU value across all user infrastructure. But it can also be used to avoid the extra cache miss I talked earlier when we want to enable receive mergeable buffers. Because if we know that the host will never send packet larger than the descriptor buffer size, we can just disable the feature at initialization time. And so we save this extra cache miss. Another feature that is being reviewed on QEMU mailing list currently is vhost PCI. So maybe it will be in DPDK 70.5, but it's not here yet. The idea is simplified here. So when using a traditional way to transmit a packet from one VM to another, the packet goes to the host, vSwitch, and vSwitch will transmit it to the second VM. When using vhost PCI, the vhost PCI device maps directly, connect directly to the second VM virt queue. So it's a little more complex than this because you have to set this up. And so it requires the introduction of a new protocol, the vhost PCI protocol, and QEMU run the server on the first VM, and the second VM will connect to. The advantage is that it improves the performance, of course, because the two virtual machines will share a single virt queue, and so the packet does not have to be copied multiple times. And there is no change needed into the virt.io guest because of its design. But it has some disadvantages that we have in the first release, that on the first version that is being reviewed today, is our security challenges because the first VM will map all the second VM memory space. So if you don't trust the second VM, this is something you cannot use today. And this is something that could be solved with IoTLB features. So Victor will talk about this after. And also there are some concerns about the migration because your two VMs, the two QEMU instances are connected through a socket. So it might be at some complexity to perform a migration. Okay, so now I will let Victor talk about some security stuff.
Okay, so to achieve high performance, we have several solutions. One of them, vhost PCI, which maps directly part of memory from one guest to another guest and implement in DPDK library the functions to access virtual queues. Another solution is to enable networking from VM to host user space. It's vhost user. But again, to achieve high performance, we map the whole physical space of guest to user process and to enable to access any buffer in any place. And it's not secure. It's not isolated. If you think about two VMs, you cannot trust another VM from bugs or from some malicious software. When you talk to some process on the host, in theory it's better. You can consider it as trusted, but still, if it's some third-party user process, it can have bugs, and it's not healthy to give the access to the whole physical memory. So how we can fix it? On the host, we have a notion of IOMMU. And IOMMU, one of its features is to restrict the access to the physical memory on the computer from devices, from physical devices. Since physical device today can have firmware, can have bugs, and also if it's on the fault, it can overwrite some places on the physical memory of host. And modern processors, both AMD and Intel, each of them support different mechanisms that enables every access from the PCI bus to undergo some address translation. And it's IOMMU, and it's implemented in real CPUs. So when we talk about virtual machine, for today there is no any support for translations of guest physical address, guest user space address to guest physical addresses. And if we want to supply such a feature, we have to implement IOMMU emulation in QEMU and KVM. And this feature is going to be added both to the KVM and the DPDK. First of all, I would like to explain how it's going to work in case of vhost, when it's sitting in the kernel memory of host. So the basic idea is quite simple. QEMU represents the machine to the guest operating system like it does support IOMMU, and then VM can start using it by means of IOMMU driver. And from that point, every physical descriptors to the network card will include guest logical addresses to the memory instead of physical addresses. And that means that when we work with buffers, every such address needs to be translated from guest logical address to guest physical address, which is the same as host user space address. And the knowledge of such translation table is sitting in QEMU, since QEMU handles TLB requests. And the actual accesses are performed by vhost, which sits in the kernel. So the kernel, each time he sees a new address which needs to translate, just send the question to QEMU about how to translate, and for following accesses just caches this translation information. Another mechanism that needs to be explored when VM unmaps the DMA memory, the QEMU sends the invalidation request to vhost just to let to vhost know that this address is not more in use, and next time vhost need to ask again if it sees the same address. So it's the basic idea, which going also going to be included in the probably next release of QEMU and KVM. And to support this for vhost user backends, the basic idea is the same. The difference is that to communicate is the means how we communicate information about IoTLB translations and about cache invalidations. So again, the backend has to keep some kind of IoTLB cache, and each time it see a new IO virtual address, which it don't know how to translate, it just ask QEMU, but this time by means of Unix socket, and also IoTLB cache invalidations are sent by means of Unix sockets. It's slightly slow, but it's still not in main data paths, so it doesn't affect much the performance. So the conclusion, the DPDK is now under active development to support various features for virtual machines. We think that 10 megabit packets per second is really achievable with DPDK running in VM and on the host to supply VM to VM communication. And we think these features are crucial to support industry transitions to NVF SDN networks, since both the security and high performance are very important for this. Thank you very much. And now we have time for questions and answers. So, was it interesting? Now we have time for questions. Yes?
Okay, you explained it a bit why zero copy is a security problem, and I agree with that. And although copy is very expensive, I was considering if it would be a good idea to have some sort of a copy on write implementation, so we could not copy when going to DVM, and then if DVM decides to do something with the packet, then we trigger the copy. Because for the DNF case, well, there might be router switches that they don't do anything with the packet.
Repeat the question.
Okay. So the question was just maybe we can use some copy on write and eliminate this way the copying of buffers. And I think Maxim could explain about feature of zero copy, which I think does pretty much the same.
Actually, this is something we haven't considered yet. So maybe if you have good ideas, we could discuss about this.
Yeah, I did another experiment. If you measure the time that the packet takes to go from the NIC to the side of the VM, and takes out the virtual IO when it goes inside of virtual IO, and out simply shortcutting all the virtualization stuff, I get an estimation about 8 million packets per second. When I have everything included, it's about 3.5 million packets per second. So I thought that vhost user would be happy. Then I implemented another PMD device, which does not use vhost at all, just share memory with the guest, and I got the same numbers. So that showed me that vhost user is light. It seems to be fast enough. But something else, like the virtual perhaps PCI is not working or not fast enough. I don't know.
Yeah.
Maybe you guys have looked into the virtual internals and PCI stuff.
Yeah. So the question was about that. Actually, the vhost implementation is quite efficient, since you can achieve about 3 million packets per second. It's still lower than we want to reach. We want to reach 8 or 10 million packets per second, and we're looking for possibilities since your measurement and our measurement show that 8 to 10 million packets per second are achievable when you use some shared memory. And both DPDK on both sides, right? So that's exactly the point. I think that you measured only 3 packets per second VM to VM because all current implementations still need some immediator in OVS, and there's what we call the zero copy eliminates only copy from virt queues to mbuffs. But there's still one copy from one virt queue to another virt queue. And this, which lowers the performance, and we're going to address this by VirtIO PCI devices, which will enable us to map directly the ring buffers of one guest to another guest. And this way, we eliminate this last copy of that elimination of OVS. It's in reality, it's much more complicated since if we want still to have some switching capabilities, we need to implement some small switch inside DPDK, which will reroute this traffic directly to the buffers of another VM or down to full OVS on the host. But it is the way, since if we want to have NVF and SDN on using virtualization and virtual machines, we have to supply them with this kind of performance. Since the only things that it's just trade-off between flexibility that NVF require and high performance, which till now only bare metal solutions could supply. And we're still not there, but we are going to that direction, to supply bare metal performance with flexibility and security of VMs. Any other questions? Please.
Just curious, do you know if DP host thread in the kernel works with supports busy polygon?
I don't know.
I think JSON is working on it, so you should have JSON.
Okay, the question was if vhost implementation, current vhost implementation supports busy polling to
in the kernel.
And okay. If there's no more questions, so thank you very much for your interest.
Thank you.
What? The batteries out?
No, yes. Tick is
Yeah.
This is very dangerous. This was not well designed at all.